Okay, so let's start. Okay, so good afternoon, everybody. So last time I told you any logic. Let's start. I told you last time any logic expression I can write it in the format of POS, product of sum or sum of product. Okay, so SOP, which is sum of product. Okay, so also that's what I'm going to explain. Also, I can put any logic expression in POS, product of sum. Okay, and I made it clear last time. I don't know why, but they use the wrong expression. So here, product, it doesn't mean multiplication, it means AND gate, because we don't have multiplication here. Sum here means OR gate. Okay, so what sum of product means? Okay, so it means if equal to expression or sorry, a term or term or term and so on. Okay, so I have multiple terms, all of them are all together. Also, I told you every term here is actually in the format either it's only one variable like A or multiple variables but AND together, AND like A, B, C, A prime, C, whatever, okay, something like that, okay? That's why it's called sum of product, because here we have product, and then I sum together, okay? This is what's called sum of product, okay? So I give you one example here. For example, I can say F equal to AB or B prime C or EC, just an example, okay? So if again, any function in this format, I call it SOP. We agree on that, okay? And if any function, any expression, I can put it in this format, okay? Either, as I'm going to explain, any function I can put it in this format, either by algebra manipulation or by truth table, as I'm going to explain. But for now, you should know any function I can express it in this format. Okay. Now, if I want to implement this function, so I need only one OR. Okay. And then here, for every term, I need one AND. So here I need one AND. AB, I need another AND here for B prime C, and I need another AND here for EC. Is that okay? So it's AND, and the output or together using only one OR. Is that okay? Let's go to the second one. Again, any expression, I can also express it in product of sum. Okay? So what is product of sum? Again, it's almost the same thing. I have here one term, so F equal to one term and another term and another term and so on. Okay? That's why it's called product. And inside every term here, either it's only one variable, something like A, or A or B, A or C, A prime or B, something like that. Okay, so here in every term, we don't have multiplication, only OR. Okay, so for example, it's wrong to have something like that. A, B or C, no, it's wrong. So you have to be all together to call it product of sum. So here we have sum, we only use sum here, or we only use OR here, we only use OR here, we only use OR here, and then all of them are product. Okay, product here means N. So in order to implement this function here, let me give you an example, and then I will show how we implement it. For example, if I have here a function F equal to A or B, ended with something like B or C, okay? Ended with A prime or B prime, okay? Any function. this one. So to implement this one, I need only one AND. Look here, here I need only one OR. Here I need only one AND, okay? And then every term, I need one OR for every term. Here I need one AND for every term. Is that okay? So I need one OR. So here we have AB, here we have BC, here we have A prime, B prime, and then this F. Any question here? So again, what I'm saying, any logic expression, I can express any expression in one of these two formats. Okay? Or actually I can any function, I can write it in this one or this one. So both of them are okay. Is that okay? What I didn't explain yet, number one, how, if I give you a function, how can you express it in these two formats? I didn't explain this part yet. Also, what I didn't express yet, okay, what's special about this format? Why is this so important? Okay, I'm gonna tell you now why this is important. Look here, guys. Actually, the importance of this format is there are two reasons. Let's start with the first reason. The first reason is this format here, sum of product, is equivalent to, so if I have here this one, we call it AND OR. So we have AND and then we have OR. Okay. So this one is equivalent to, if I use NAND, then we have here AB, another NAND, I use here B prime, C prime, another NAND, I use here AC, and then everything together connected to NAND. So these are equivalent. So again, any AND OR is equivalent to NAND and AND. It's the same thing. Is that okay? Can you prove this to me? Very easy. Yes, I can give you a very simple example to prove it. Okay. For example, here I have AB, I have here OR, I have here CD. Just for example. So here F is equal to AB or CD. Is that okay? Let's see if the other one, NAND is equivalent to this one or not. I'm gonna use algebra manipulation to do that. So here we have AB, we have here CD, everything connected to one NAND. Okay, let's see. You know, what we have here is actually AB prime. What we have here is actually CD prime, okay? And then what I should have here, F should equal the first term, which is AB prime, ended with the second term, CD prime, okay? Everything is prime, because it's NAND. Any NAND, the two inputs end together, and then you make prime here, okay? So now, I'm gonna use De Morgan. So if I use De Morgan, the first term, I'm gonna invert it. So this one should equal AB prime, prime. And then any N should be OR. The second term, CD prime, I will invert it as well. This is De Morgan. So here, inverter with inverter cancel each other, inverter with inverter cancel each other, so it should equal AB or CD, which is the same thing like this one. Okay, so again, what I did right now, guys, I proved to you using algebra manipulation. You can use truth table, as I said before, but maybe it's easier for me to do the algebra manipulation here. So I proved to you if you have AND or it's equivalent to NAND. It means if you have here, this is AND, multiple ANDs here, and then everything is OR together. This one is the same circuit if I use here NAND. Is that okay? Is that clear? Again, why this is interesting? It's as I told you in before. When I manufacture chips, it's more efficient, it's better if I can implement the whole logic circuit using only one gate. For example, in this case, it can be only NAND. In electronics, if I have one good electronic circuit for NAND, I can just keep using it to create a logic circuit. It's much easier or more efficient. Okay, guys? And this is, if you remember last time, I told you the reason I'm explaining NAND is because I can implement any circuit only using NAND gates. Is that okay? Any questions? Okay, let's go to the other one here, which is a product of sum. Okay, so product of sum here, it has this format. So I will show you right now, similar to what I did here. I will show you. Okay, so what I have explained is any expression sum of product, it can be implemented only using NAND. That's what I explained. Okay. Same thing I will do here. So any expression that is in product of sum, it can also be implemented using NOR. So this one is NAND, this one is NOR. You got what I'm saying? So this one or AND. So if you have, I'm gonna repeat everything again, but for the new one here. So if you have here or AND, which is you have AND here, and then you have here OR. Here I give you expression for only 2 terms, but still it's okay for more than 2 terms. So for example, if you have here AB, CD, the output here has to be A or B and C or D. So this one is equivalent to if I use here NOR and if I use here NOR, this one. So here, A, B, C, D. The output here will be the same like this one. Can you prove this one to me? Yes, I can. So if you look at what you have here, it should be, in case of NOR, as I explained last time, the input A or B inverted. Here, the input C or D inverted. And now F should equal A or B inverted. Or C or D inverted, and everything is inverted. So the 2 inputs, you add them together and you invert. Again, if you use De Morgan, in De Morgan I have to invert the first term, invert the second term, and then any OR, any AND becomes OR, any OR becomes AND. So this one, if I invert this one, is cancelled. If I invert this one is cancelled. So it should be A or B and C or D, which is the same thing like this one. Okay, guys, any questions? Yes, sure.
So you can go from regional products and product sums by using De Morgan?
No, I use De Morgan because of the inversion here. If you have inverter here, I can use De Morgan. Okay. I use De Morgan because you have inversion here. So what De Morgan is telling us? De Morgan is telling us if you have A, B inverted, so this one should equal to, you have to invert the first term, you have to invert the second term, and because the relation here is AND, should be OR. If it is OR, it should be AND. So I just apply De Morgan for manipulation, algebra manipulation. Okay, before we proceed, let me summarize what I said. What I said here, guys, any function or any logic expression, I can express it in a product of sum or sum of product, okay? So it can be both, by the way, so you can have the choice. So any function can be this one or this one. It can be both or both. So you can express it in any one of these forms. Okay? In sum of product, so it's actually AND or. Okay, so here you have sum, you have product, and then you have here sum. Okay? And actually, as I told you, if you have AND or something like this one here, I can do it using NAND. Okay? In other words, if you have a function and you want to implement this function using NAND, so I have to write this function in SOP format. Okay? Same thing here in product of sum. Product of sum, this is how it looks like. So for every term you will have or, and then everything connected together using and. Okay, that's why this one is called or and expression. And or and expression is actually similar to using nor. Okay, so in other words, if you want to implement a function using nor, so you have to put this function in the format of product of sum. Is that okay? Any question? So now, what I'm going to explain right now is how, if you have an expression, how I can put it in product of sum or sum of product format. I can do that using either algebra manipulation, or I will show you if you have a truth table, how can you write the function from the truth table in any one of these two formats. Is that okay? You will see right now. So here, yeah, let me go through this part. So here I'm making definition what is sum of product. I told this here you have and then you have or here. Here I'm showing you I want to put this one in sum of product format. So I'm going to use algebra manipulation. So what I did here, I did distribution. As you see here, after I did this, it's already now in some. It's already in sum of product format already, but for sure I need to do simplification. So when I do simplification, I will give it to you. So it's I can do simplification at the very end. I can reach to this format. So here, although I started, this format is not sum of product or product of sum. Why? Because in this term I use and use or. What you say? I'm very clear. In case of sum of product, in every term, you have to use and, or either use and or only one variable, okay? But in case of product of sum, so every term here, you have to use or, only or. But here in this case, this format is not sum of product of sum. I can do some algebra manipulation, as you see here, to put it in this format, in sum of product format. This is product of sum, as I told you. So it's or, and then after or I put and. Okay. Same thing here. I give you this function here, and I want to show you how I can do algebra manipulation to put this one in a function in a product of sum format. And actually, what we're going to do here is actually this. We're going to use this rule. In this rule, as you see here, we do distribution for the or. You remember this one when I told you we don't have this one in the normal algebra, that's why usually we forget it. So here I can do distribution this way, and that's what I did. Okay. So anyway, that's what I will do right now. So if you see here, I give you this one here. This one is product of sum, and I want to put it in sum of product. Okay. So what I can do here is I can do consider this one term. Another term here, so I can do distribution as you see here, okay, and then so this term is already okay. This term is okay, so I need to work on this term. So I can do distribution again, okay, this one. So that means I can put it in product of sum. Okay? This may not be the most important part. The most important part is if you have a truth table. How can you write the function of the truth table in product of sum or sum of product? This is the most important part, okay? So here I'm saying sum of product, you can put it end this way. So that means NAND is equivalent to and or. So if you have and or, NAND is the same. Same thing here for a product of sum, okay? That's what I explained. So if you have no, you can or and is the same, or and it's the same thing. I can implement it using no. Okay. Any questions? So again, we agree now. Any logic circuit, I can implement it only using NAND gate or only using NOR gate. And I think that's what they do in industry. So they do it this way. Okay. So if you have a good circuit for NAND, I can use this circuit to implement the whole circuit, the whole logic circuit. Okay. One more thing here, but maybe this is not the main reason, but this is also one of the reasons why we like sum of product or product of sum. Why we like it more than something like that. So this one is not this expression. It is not sum of product or sum of or product of sum. It's not. It's neither one of them. Okay. So if I implement this function this way, okay, or I can put the same function in sum of product this way, okay. So this one usually it's better for me, okay. Again, I told you there is one reason. I will explain one reason. The reason is to implement this one, I can only use one type of case, which is named. Okay. There is another reason. If you see here, what is the speed of this one? What is the speed? Usually, when we talk about the speed, you have to look for the longest path. Longest path. So I have here one delay, two delays. So I'm gonna assume all delays are the same. So I'm gonna say TP, and another delay here TP. So to get the output here, I need 3 TP. This is the delay. Okay. Someone can tell me, but you have a path here. You have, yeah, but this is just true. I'm not gonna get the correct output here. Usually I look at the longest path because I'm not gonna get the correct output. Yeah, this one, this the correct input will come fast. But to get the correct output, I need to wait for this input here. Okay. But anyway, so we need to look for the longest path. Here, the longest path is always fixed. It's always 2 TP. So here I need a delay here and I need a delay here, 2 TP. Because all these gates are going to work at the same time. So all these gates are working in parallel. So all of them are going to work on the same time. So I'm going to need one delay here and one delay here. This may be another reason why you will like sum of product or product of sum. Yes.
Isn't the final OR gate with the 3 inputs, isn't that equivalent to 2 OR gates?
Yeah, that's a good question. Yeah. So the question now is a very good question. So the question is, so this actually is equivalent to, I'm gonna take 2 here and then make 1 gate and then take another one, make another gate. So actually, although I'm writing it in 1 gate, it's actually 2 gates. Okay. So my answer is yes, these 2 are equivalent as a function. Okay, as a function means the output here, okay, the relation between input and output here is the same thing like the relation between input and output here. Okay, but when I manufacture it, in manufacture, I don't need to make it this way. In manufacture, I'm going to do it only using one logic circuit. Okay, in the coming lab, I give you one example. Just again, electronics is out of the scope of this course, but sometimes from time to time we need to touch it. Okay, so in the coming lab, I give you one circuit for named. So the way I did it is, you have here one transistor this way, and then another transistor this way, and then you have 2 inputs. Okay. So if I want to make one name with 3 inputs, what I can do? Okay, very simple. Just add one more transistor here. You got what I'm saying? So now it becomes like named with 3 inputs. You got what I'm saying? Okay. Yeah. So this is a summary. That's what I explained. Now I'm gonna come to the most important part because this is what we will do also time. This is the most important part. Okay. What I want to explain now, guys, is given a truth table. If I have a truth table like this one, so I have inputs and I have input for a function. Okay. How can I write the function? Okay, in the format of SOP or POS. Okay, so what I'm going to explain now, given a truth table, how can you write the function in the format of POS or SOP? Okay, let's start with the first one here, SOP, sum of product. So in sum of product, I'm going to make it very simple. I give you here, you have this truth table here, okay? So I want to write this function in sum of product, SOP. Look at the idea. I don't want to memorize anything, but you need to understand it. Once you understand it, it will be easy to memorize it, okay? Look at the logic. This course is about logic, and that's true. Everything is logic. There should be logic in this course, okay? Anyway, so let's see how it works first. What is the main idea? How I'm going to write a function, this function for f. Again, what you learned so far in this course, what you learned so far in this course is the opposite. If I give you if, how can you make the truth table this way? That's what you learned in this course so far. Now I'm gonna do the opposite. If I give you a truth table, okay? If I have a truth table, how I can get a function out of the truth table? Using sum of product and product of sum. And the two functions are equivalent. They are doing the same thing. It's up to you. You want to implement this one, you want to implement this one, it's totally fine. Whatever, both of them are doing exactly the same thing. Okay? Let's start with sum of product. So the way we have to do it is, you have to go to if here, this is a function. You have to look at the ones, not zeros. I'm going to tell you why. You have to look the ones. Every one, we don't work on zeros. In case of sum of product, we only work on ones, not zeros. In product of sum, when I explain it, we work on zeros, not ones. But now I'm talking about SOP. In sum of product, number one, we have to work on ones. That's number one. Number two, every one you have here should be one term. So here, this one here, this one is going to contribute to the function by one term. So yeah, this term here. This one is going to contribute by one term, one term, one term, one term, and all of them ordered together. Okay? So the number of terms I have is equal to the number of ones we have in the function. Is that okay? Okay. So so now you are telling me for every one here, I have number one, I have to work on the ones, not zeros. Okay. For every one, I have to get a term. For everyone, I have to get a term, and then I have to all of them together. That's true. Okay. Tell me, number one, how can you get these terms? And what is the logic behind it? Why you work on ones? What this term will do? How it works? I'm gonna tell you, but let's start with this one. So here, when this is the input, look here, guys. If this is the input, I want to get one. I need AND gate that give me one when the input is 0, 1, 1. I need AND gate because I told you every one here is going to contribute by one AND gate. So this one is going to contribute by one AND. The second one is one AND, and so on. Okay. So here, when the input is 0, 1, 1, I need this AND gate to give me one. So what I should put here in the input? You know, this is how AND works. To get one at the output of AND, all input should be ones. Okay? So very simple. Whoever one, I will keep it like you have B, it's gonna be B, C, and then I'm gonna make it A prime. Why you make it A prime? So that when I get 0, 1, 1, this 0 becomes 1 because I'm taking prime for this one. B, C, all of them are 1, so this AND will give me 1. Okay, let's see another one. So for example, so this, I'm done with this one. I'm gonna make one AND give this one. Look at the second one here. It's the second one. Okay, so here I want this AND. So this AND the number 1. I'm gonna put this one AND the number 2, and this is number 1, this is number 2. Okay, and AND the number 2. I want this AND to give me 1 in this specific input. When the input is 1, 0, 0, this is specific input. Okay? So any 1, I will keep it the same. So here A, any 0, I will have to make it prime. B prime, C prime. So that when A is 1, this input is 1. When B is 0, this term becomes 1. When C is 0, this term becomes 1. And this AND give me 1. So this AND will give me 1 in this specific input. Let me ask you a question. What about the other inputs? When the other input comes here, what do you think this AND will give me? Give me 0. Okay, so I designed this AND to give me 1 in only this specific input. In any other input, it will not happen that all inputs are ones. Because I made the input only to give me 1 here. When When this one is 1, 0, 0, this bit will give me any other case, for sure, this bit will give me 0. Okay? So this is gate number 2. Okay, so I'm done with this one. This is gate number 1, gate number 2. Let's go to, for example, gate number 4. I will repeat it again. So here for this one, I'm gonna make another gate here, gate number 3. Okay, and the inputs here for this one, yeah, this one is 1. So any one, I'm gonna take it without inversion. Any 0, I'm gonna take it with inversion. Any one here, I'm gonna take it without inversion. So that when I have this specific input, this end will give me 1. And any other input, this end will give me 0. So again, make it very simple. What I'm saying is that number 1, I have to work with the ones, not the zeros. That's number 1. Number 2, for every one, I'm gonna design end. This end is gonna give me 1 in this specific input, 0 for any other input. Okay. Okay, so this is end number 3. I'm gonna repeat it again. I'm gonna make one more end for number 4. Yeah, here is number 4, here number 5. So let's look at this case here. Okay. Here you have here A, B, and C prime. Okay, so it has to be A, B, C prime. So again, when the value is 1, I'm gonna take the same variable, the same input without inversion. If it is 0, I'm gonna take inversion so that I will get 1 here in this specific case. Okay. Last one here, 1, 1, 1. So in this case, which is case number 5, it has to be A, B, and C. And then I will OR everything together, and this is F, the function. Okay? Okay, now make it simple. What is the logic? What is the logic? Okay? It's very simple logic, if you understand, very simple logic. The logic is, if this is the input, gate 1 will give me 1, other gates are gonna give me zeros. And because this is OR, it is enough to have one input, 1 to give you 1. So this, the first gate here will be 1, give me 1 in this specific input. Okay? If in this specific input, gate number 2 is gonna give me 1. The other gates are gonna give me zeros. And because this is OR, it's enough to have one input is 1. Okay? So gate number 1 is gonna be activated. Activated here means it's gonna give me 1 in this case. Gate number 2 is gonna give me 1 in this case. Gate number 3 is gonna give me 1 in this case. In any other case, it's gonna always give me zeros. Okay? By this way, I guarantee the output will be 1 in this case. Because I designed one gate to give me 1 in this case. I designed one gate for this case to give me 1. I designed a gate for this one to give me 1. I designed a gate to give me 1 here. I designed a gate, so I guarantee for these inputs, I guarantee the output will be 1. But the question is, do you guarantee for these inputs you are gonna get zeros? The answer is yes. Why do you guarantee? Simply because every gate here is gonna give me 1 just only in one case. So this one here. So in any other, so this gate here, gate number 1 is gonna give me 1 only in this specific case. If you change the input to anything else, it's gonna give you 0. You got what I'm saying? So this end is here, every end here will give you 1 only for one specific input. Any other input gives you zeros. Okay, guys, so make it simple. Number 1, if you have a truth table, how can you write the function in sum of product? Step number 1, you have to work with the ones as I explained to you. Okay, the number of AND gates you have is equal to the number of ones. For every one, you have to write one expression. So in this case, I should have 1, 2, 3, 4, 5 expressions. Okay. For every expression, the way you have to do it, I have to do it using AND because this is sum of product. I have to do it using AND. Okay. And the way you have to make sure this expression you are gonna write it using AND is gonna give you 1 in this specific input. To do that, Any variable that is 1 here, I will keep it without inversion. So here it's gonna be B, this one should be C, and any 0, I'm gonna use the inverted one. So that I can get all the inputs are ones for AND to give me, that's all to give me 1. Any questions? Okay. Okay, any questions? By the way, this function is like a raw function. It is not simplified. You got what I'm saying? So what I did here, I got a function. I didn't care about simplification. I just got a function that can give me this truth table. I give you the, remember, I start with the truth table. I have a truth table. I want to get a function out of the truth table. We didn't do that before. All what we did in this course is the opposite. I give you a function and then you make the truth table. Okay? Now I have the truth table. Now I want to get a function. So I will get a function this way, but you need to keep in mind this function is not simplified. So we need to do simplification for sure for this function. But this is how can I do simplification? Either in this chapter using algebra manipulation, or in next chapter I will explain key maps, another approach to do simplification. Any questions? Okay. Now, how can we do product of sum? By the way, it's not very different from what I explained. It's still the same logic. In product of sum, so here you have AND, and then here you have OR, here you have OR, here you have OR. Okay? So this is a product of sum. One of the, so here, one of the differences between sum of product and product of sum, this time I'm gonna work on ones, not zeros. I'm gonna work in zeros, not ones. Is that okay? Okay, that's okay. And again, it's almost the same idea. It's almost the same idea. So here I have 3 zeros. For every 0, I have to make one term here that has OR. This one has to make one term here, and this one has to make one term here. Is that okay? Okay. So how? So again, it's the same thing for every so here I'm gonna make a function that has 3 terms. If I express the function in product of sum, I will have 3 terms here. But if you want to do it using sum of product, you have how many? 5 terms. Okay, maybe, and both functions are doing the same thing. You understand what I'm saying? So both are the same, but maybe in this specific case, a product of sum is more efficient because I have only three terms here. Here I had 5 terms using sum of product. Okay, anyway, so it's almost the same idea. The idea is for every 0, not 1 here, for every 0, I have to make a function. Okay, but how I'm gonna make a function? For every 0, it's 1 term, and I have to express this term using OR. So how you will do it? Okay, the way you have to do it here, you have OR. I have to select the inputs for every specific term, so that it gives you 0. So the term I will use here, I have to select the inputs so that it gives me 0 in this specific case. In any other case, should give you 1. So this OR here should give me 0 in this specific case. This OR here should give me 0 in this specific case. This OR here should give me 0 in this specific case. In any other case, they should give me 1. Okay? So how I can do that? How I can express if you have OR here in this specific case? How I can get 0 in this specific case? Very simple. You know, in case of OR, in order to get 0, all inputs should be zeros. So whoever 0, I will keep it without inversion. So here in this specific case here, I'm gonna write ABC. Okay, so now write ABC. This one will become 0 in this specific case. When it is 0, 0, 0, okay, I will get 0 here. I think something is wrong. Yeah. So here, yes, so I have to make sure, in order to get 0 here, I have to make sure all inputs are zeros, okay? So it has to be A or B or C in this case, okay? Let's look at the next one here, how I can make sure the OR, again, I make it easy. Number one, you have to work on zeros, not ones. This is number one. Number two, for every zero, you have to make one term. And all these terms are ANDed together, okay? And when you select this term, you have to select this term using OR, because this is product of sum, so it has to be OR. And you have to make sure you have to select the inputs in such a case, in such a way that it gives you 0 in this specific case. Okay? So look at the second one here. How I can make OR here? So this OR give me 0 in this specific case. Okay? So A, I'm gonna keep A, I'm gonna keep B, but I'm gonna make C prime. So that when I get 0, 0, when I get 1, I'm gonna invert this one to become 0, so that all inputs are 0 to get 0. Okay? Same thing here for the last one here. I'm gonna make it using OR. So again, whatever 0, I will keep it without inversion. Whatever 1, I will invert it. So this one should be A, B prime, C. Okay? And that's it. So if you see here, this is the final function here. It is in a product of sum. Okay. What is the logic? Tell me what is the logic behind this one. I'm gonna tell you what is the logic. Very simple logic. Look here, guys. This is AND. Is that okay? This is AND. To get a 0 here, at least one input is 0. To get 0, at least one input is 0. Okay. I designed this OR to give me 0 only in one case and give me 1 in all other cases. You have to understand this way. I designed this OR here to give me 0 only in case of one input, only one input. All other inputs will give me 1. When you go in, you can check it. You will find it works this way. Okay? So here, at least I need to receive 0 here to get 0. So in one case here, because I have only 3 zeros, in this case, 0 will come from here. Okay? So that's why I guarantee I get 0. In this case, if this is the input here, the second OR is going to give me 0. That's why I guarantee I will get 0. In the third case here, this input, this OR gives me 0. That's why I guarantee I get 0. Okay, what about the ones? Do you guarantee I'm going to get ones? In this case, the answer is yes. Why? Because when I design this OR, I designed this OR to give me 0 in this case and give me 1s in other cases. So in other cases, this one will give me 1, give me 1, give me 1. You understand what I'm saying? Okay. Let me summarize what I said. The conclusion. I'm going to repeat it again. The conclusion is, if you want to put it in some. Can you close the door, please? If you want to put in some of the product format, number one, you have to work on ones. This is number one. Okay. Number two, the number of terms you have should equal to the number of ones. For everyone, the way you have to write the AND gate is, if you have here, I need the AND gate to give me 1. Okay, I just want you to remember this way. I want the AND gate to give me 1. So I have to guarantee all input should be 1. That's why whatever 1, I will keep it without inversion. Whatever 0, I'm going to invert it. Okay, that's why here, for this one here, I'm going to have this term here, in this case. I'm going to have this term in this case. I'm going to have this term in this case. And then I'm going to OR them together. In case of product of sum, number one, you have to work on zeros, not ones. Number two, for every case, you have to make a term that has only OR, as you see here. And you have to select either for every variable, either the variable or the inversion of this variable, so that this term, the term gives you 0. Okay? In this specific case. So that is why what you have to do If the input is 0, you are going to use it without inversion. If the input is 1, you need to invert it. Very easy, right? Very easy. So here I'm going to use A, B, C. Here I'm going to use A, B, but C inversion, which is actually you can see this case here. For this one, I'm going to use A, B inversion, C. That's it. You can see it is here. And then I'm going to OR everything together. So what I did here, this is the way you have to do it. But what I did here, it's like I proved how we are going to do it. So what I did F for prime. So this is F and this is F for prime. So then in F for prime, so I'm going to work these ones. I'm going to work here in these ones, similar to sum of product, and then I'm going to get F for prime in sum of product. So this is F for prime in sum of product. Okay, but I need F, so I'm gonna do De Morgan. Okay, so you have F for prime. I'm gonna do De Morgan to get F. If I do De Morgan, I will reach to this one. Just like a proof, but you don't need. You can do it directly. So again, what I did, guys, here, I did here. If you have F, I'm gonna make F for prime, and then I'm gonna get F for prime in sum of product, and then I get inversion. I will get this one. But you don't need to do this way. You can do it directly. As I explained, you don't need to do F prime. You can just work on the zeros as I told you directly. Is that okay? So now, guys, what I'm explaining now is if you have this function, I can express this function in sum of product, and this is the formula I can use. I can express the same function in product of sum, and you can use this one. These two functions are doing exactly the same thing. You understand? Yes, sure.
So basically opposites of each other, product of sum and sum of product.
Yes. This is how you create the function. But these two functions are doing exactly, they are equivalent. Yeah. That's what I'm saying. These two functions are equivalent. So when you go home, you can make here two tables. One for the SOP and one for product of sum. You will find what you are going to get here is similar to F if they are equivalent. Okay? Any questions? Yeah. Even I tried to prove to you that these two functions are equivalent. So this is the first function I got. This is the second function I got. Okay. So here I did manipulation in this slide. I did algebra manipulation to prove to you they are equivalent. So I started with the first one here, which is sum of product, and then I simplified it using algebra manipulation. Here I started with product of sum, okay, and then I also simplified it. So I did it here using algebra manipulation to prove these two functions are equivalent. You can also do it using truth table as well. Any questions? Okay. Okay. So now I will come to something we call it min terms and max terms. It's not very different from what I explained. Min terms and max terms. Okay. So here, if you have a function ABC this way, and this is row 0, or this is actually number 0 in binary. So this is number 0 in binary, number 1, number 2, number 3, number 4, number 5, number 6, number 7. So this is can be a row number or even the equivalent of this number in binary. Okay. So if I have one here, so we have something we call min terms and we have something we call max terms. So the terms I explained here, you remember when I worked it on ones and I got these terms? These terms are called min terms. Okay, so here these are the min terms here. The terms I got here, these terms I got here for zeros, the ones I got for zeros, the three terms, every term of them will call it max terms. Okay, so that's why here, if this is the input and I want to get the min term equivalent to this one, that means if we have here 1, if the function has 1 here, what will be the min terms here? A prime, B prime, C prime, right? Because I have to guarantee 1, 1, 1. Okay. If the 1 is here, okay, so this should be the main term here. So if the function has 1 here, what is the term I will get here? We call it main term number 1. So here we have main term number 0. Okay, this one main term number 1, which means if I have a function and I have 1 here, so this is the term I will use in sum of product. Okay, so here, so I got all of them for all numbers. So here in case of 1, again the way I did it, similar to what I explained, the term that has 0, I have to prime. Thanks. Oh, I need to. Okay. I wish. But there is no silent, right? Okay. Okay, thanks.
May I have your attention? May I have your attention, please?